So we have finally arrived at the final part of the Eigenvectors chapter. And in this part, I'm going to tell you about two very important theorems regarding eigenvectors and the fact that matrices commute with each other. And these theorems are very important because you will use them for quantum mechanics. Okay, so in here I'm going to write the theorem and also write the proof for that theorem. So the first theorem states the following. If matrices A and B are simultaneously diagonalizable, and what does simultaneously diagonalizable mean? So it means that both matrix A and matrix B can be diagonalized by using the same change of basis matrix. So let's call the change of basis matrix, let's call it V. So A equals B times dA times V to the minus 1. That is the recipe for a diagonalizable matrix, yeah? And now B can be diagonalized using the same change of basis matrix B, okay? So we have the same V for both. This means that, remember that this matrix V, which is the change of basis matrix, has the eigenvectors as the columns. So this means that they have the same eigenvectors, okay? They have the same eigenbasis. Same eigenbasis. So when two matrices have the same eigenvectors, they are called simultaneously diagonalizable. And this means that this implies that A and B commute with each other. Okay, they are two matrices that commute. So let's prove it. So we are going to assume this, and we are going to prove that AB equals BA, which means that they commute. Okay, that's our objective. So this is how the proof goes. We start with AB, A times B, and we substitute the diagonalizable versions of them. So the A is equal to V times the diagonal matrix dA times V minus 1, and B is equal to V times the diagonal matrix dB times V to the minus 1. Now we notice that these two, V to the minus 1 times V, they cancel out. So we end up with V times diagonal matrix A times diagonal matrix B times V to the minus 1. And now we realize that when matrices are diagonal, they always commute. Because remember, when you multiply a diagonal matrix by another diagonal matrix, you always get that the product is simply equal to the product of the corresponding elements. And therefore, they commute, because it doesn't matter the order. A times D is the same as D times A. These are scalars, and therefore they are multiplying and they commute. Okay, so diagonal matrices always commute with each other. Therefore, if we go back to our proof, we can now commute dA with dB. And now we can add the V minus 1 times V back. And now we can identify that this is equal to B and this is equal to A. So we have proven that A times B is equal to B times A. And the only requirement was that they can be diagonalized with the same basis. Okay? Now it makes perfect sense that if they can be diagonalized with the same basis and they commute, so diagonal matrices always commute. So therefore, this means that the linear transformations that these two matrices are associated to, they commute. So it doesn't matter if you express them in a basis of the eigenvectors when they are diagonal matrices, or if you express them on the original basis, the transformations are still the same transformations. And if two transformations commute in one basis, they commute in any other basis. Okay? So it makes sense that if they are simultaneously diagonalizable, then the matrices commute. Now, very importantly, we have proven the arrow going to the right. Can we prove, so is it possible to prove the arrow going to the left. In other words, if you find two matrices A and B that commute, can you conclude that they have the same eigenbasis? And the answer is not always, okay? However, under certain special circumstances, then yes, and that is the next theorem. So, if A and B are normal matrices, and remember that normal matrices is a specific meaning, it has a technical meaning, yeah? And the technical meaning was that A times the Hermitian conjugate of A is equal to the Hermitian conjugate of A times A. That was the definition of normal matrices. And you saw two examples of normal matrices. For example, unitary matrices were always normal matrices, or Hermitian matrices are also examples of unitary matrices, of normal matrices. Okay, so in practice in quantum mechanics, you will always work with Hermitian matrices. So this will always be true. So if this is true, then you can write the following theorem. If A and B are simultaneously diagonalizable, in other words, they have the same eigenbasis, then this happens if and only if, which means these two statements will be equivalent, A and B commute with each other. Okay, so this is only if A and B are normal matrices. Okay, so this is a necessary condition here for this to work both ways. So when the matrices are Hermitian, if the matrices commute, then you will instantaneously know that the matrices have the same eigenvectors. Okay, which is really an amazing thing to say. So let me prove it. And the proof is quite elegant. So I'm not going to do the general proof, which is a much more complicated than what I'm going to do, but I'm going to do the proof in the simpler case in which A and B have n different eigenvalues. Okay, so we are going to assume that there are no repeated eigenvalues. There are no degenerate eigenvalues. Okay, so if I assume that the eigenvalues of A and B are all different, then I can easily prove this theorem. Okay, now to prove this relation, we have to prove both this way, but also this way. Now, the proof for this way, we already did that, because here we proved that whenever two matrices have the same eigenbasis, then they commute. We did that proof, right? This was the proof. So this is true regardless or not whether they are unitary or Hermitian matrices. It's always true. So this direction is always true. But now the key question is this direction true? And we are going to show that it is true when they are normal matrices, okay? And we are also going to assume they have n different eigenvalues. Good, so here goes the proof. First, what do we assume? So we want to start here and we want to prove this. So our assumptions are that A times B equals B times A. And also we are going to assume that they have n different eigenvalues. So A times the eigenvector of matrix A, and let's label the eigenvectors with a superscript I, where I can be 1, 2, 3 up to n. Okay, so the eigenvectors of A would be VA1, VA2, VA3 up to VAn. Yeah, those will be the different eigenvectors of matrix A. But to summarize, we will just call that VA to the power, not to the power, but superscript I. Okay, so A times VAI is the eigenvalue of A number I times the vector A number I. Okay, this is basically the definition of an eigenvector and an eigenvalue for the matrix A. And we are also going to assume that the matrix B has a certain set of eigenvectors, which we call them VB superscript I, which are equal to the eigenvalue of matrix B, the ith eigenvalue, times the ith eigenvector of matrix B. Okay? So we are going to assume this. And to assume that the eigenvalues are all different. So lambda 1 is different to lambda 2, is different to lambda 3, and so on. So these are going to be our 3 assumptions. So I'm going to actually number them. 1, 2, and 3. Because now I'm going to substitute them into our proof. So using these 3 assumptions, I want to prove that A and B have the same eigenbasis. Okay, so basically I want to end up proving that the eigenvalues of A are the same as the eigenvalues of B. Okay, that's what I want to prove. And this will mean that they have the same eigenvalues and therefore they are simultaneously diagonalizable. So how do I prove that? Let me start by writing matrix A times matrix B times the eigenvectors of matrix A. Okay, I start with this expression. Now I apply our first assumption that the matrices commute, number 1. So this means that this is equal to B times A times the eigenvectors of matrix A. Okay? Now I apply our assumption number 2, which is the definition of eigenvectors for matrix A. So here you can see that we have A times an eigenvector of A, and you know that A times an eigenvector of A is necessarily equal to the eigenvalue times the eigenvector. So therefore, this is equal to B times the eigenvalue of A times the eigenvector of A. Okay? And since this is a scalar, we can move it to the front, right? Because the scalars can always move between the matrices and the vectors. So this is equal to lambda AI times B times the eigenvector of A. So far, I have just applied the different assumptions, starting off with this simple multiplication of 2 matrices and 1 vector. Now let me write the left-hand side and the right-hand side on a single line. So I can write this A times B times VAI is equal to lambda AI times B times VAI. So I have written that there, okay? And now let me add a parenthesis. Let me move this away. So I'm going to add a parenthesis here. And what do you notice now? Now you notice that this expression, it can be compared. So compare this to expression 2, to our assumption 2, which is the definition of the eigenvectors of A. So you can see that A, matrix A, times something which is a vector, because this is a matrix times a vector is equal to a vector. So this is something that is a vector, is equal to the eigenvalue of A times the same vector. So what do you conclude? You conclude that B times the eigenvector of A is also an eigenvector of A, because this is the definition of an eigenvector, where this is an eigenvector. Okay? And since the eigenvalue is the ith eigenvalue, we know that the eigenvector must be the ith eigenvector. Okay? So therefore we know that B times the eigenvector of A is also the same eigenvector of A, but perhaps it's scaled by some amount, mu times the eigenvector of A. Why did I add this mu here? Remember that if V is an eigenvector of a matrix with a certain eigenvalue, then any multiple of V is also an eigenvector with the same eigenvalue. Yes? Remember that eigenvectors can be scaled. So this means that this vector here is either equal to the original eigenvector or to a scaled version, and that's what we are writing here. So B times the eigenvector VA is equal to a scaled version of the eigenvector VA. Okay, just by comparing this to our assumption 2. This is a very subtle proof, and I think it's beautiful. It's very, very nice. So now what can we say? Well, if you look at this equation and you compare it to equation 3, suddenly you realize that the eigenvector of A is also an eigenvector of B, because this is the equation that defines eigenvectors, right? So comparing it to 3, you realize that this scalar coefficient that we were saying, this will simply be the eigenvalue of B, but this vector here will necessarily be the eigenvector of B. And therefore, you can say that VAI must be equal to VBI. So the ith eigenvector of A is equal to the ith eigenvector of B. And this is true for I equals 1, 2, up to n. We can repeat this process for all the eigenvectors. Okay? So there you have it. Starting from the fact that they commute and that they have different eigenvalues, we proved that they are simultaneously diagonalizable. Okay? So this is it. This is the theorem that will appear in quantum mechanics next year, and at least you can go back to the notes from first year maths. I remember Paco showed this to us, and he proved it, and you have the proof right here. Okay? So thank you very much for listening, and see you in the next week for the next chapter.